Okay. So the orange line is called the what? Apothem. You can also pronounce it Apothem, but Apothem is better because it sounds like Gotham. We commonly use a lowercase a to represent the apothem. Okay, just so we're on the same page. What's the blue line? Radius. Little r. By the way, as a side note, what would that segment be called? Diameter, correct. Okay. Then we're going to call this side length S, because that's the standard in regular polygons. The side length is X. And then the last thing is we're going to call this little guy X. Okay. So now we're all standardized. Whenever we want to find one of those distances, we can use that notation, and we are good to go. Any problems so far? No. Good. Now the fun part. David, how did you find the area of that octagon? What method did your group use?
We did 1/2 base times height times the number of sides.
Okay, so let's take it from the start. What chunk of information, or I should say, what side did you? What am I doing? There we go, eraser. What side did you measure? Did you start with the apothem? Did you start with the side length, or did you start with the radius? Side length, and that side length is how long? 4 point something or another? 4.2. Okay, so you started with this distance, S being equal to 4.2. All right, so how many groups started with a side length? Raise your hand, please. Okay, just 2 of you. How many groups started with the apothem length? Raise your hand. And I assume the rest of you started with the radius, yes? Okay, good. So let's hear how they did it first. Are we all in agreement that the goal is to find the area of a triangle? Okay, now, question for you. Did you find the area of the right triangle or the area of the isosceles triangle?
The right triangle.
The right triangle. Okay. How many groups found the area of the right triangle? So or did you do the isosceles?
Yeah, the right triangle.
Okay. By the way, what's n in this case? Remember what n stands for? Yeah, it's 8. Good. It's an octagon. If there's 8 sides to the octagon, how many isosceles triangles are there? 8. How many right triangles are there? 16. Okay, so you did the right triangle.
Well, we saw for one of the right triangles, but we ended up getting isosceles.
Okay, so talk us through it.
So, first we did 360 divided by 8 to get the vertex angle.
Okay. So you found this angle.
Yeah.
Okay, we're going to call that angle alpha. Sorry, I lied. We're going to call that angle theta. So theta, you said you took 360 divided by 8,
Yeah.
which was that, right?
45.
And found that to be 45 degrees. Okay? I'm with you.
Well, then there's like the right triangle, and then we just cut there in half, so 22.5.
Okay, so then this is 22.5 because in an isosceles triangle that altitude bisects the angle also. Okay, good.
67.5 at the bottom right.
Okay. All right, now let's stop a second. I don't know if it happened in here, but I know at least a couple groups during the day found the 67.5 angle first by doing n minus 2 times 180 divided by n to find the measure of each angle in the octagon and then divide it in half to find 67.5. Personally, I like their method better, but if you use the other one, it's another approach to solving the problem. Okay, back to you.
we just did law of sines, so could have done like 22.5,
Well, first of all, how long is this?
4.2.
No,
I'm sorry, hold on.
2.1. So notice that x is equal to s divided by 2. Okay, so this is 2.1. And you did law of sines to find the apothem or to find the radius? Find the apothem. So you did sine of 67.5 over a is equal to sine of 22.5 over 2.1. Correct? Good. Then you got a value for a, which was?
5.1.
Which I assume you stored that value.
Yeah.
Good. Then what?
They just did they just did 1/2 times the base 4.2 times 5.1 the height, and then times 8.
So you found the area of the isosceles triangle and multiplied by 8.
Yeah.
Perfect. Okay. Any problems there? Who did it differently? Andy, what did your group do? Same thing. Anybody different?
We started with the radius, but we kind of did the same thing.
Right. Okay, so let's talk about the radius problem, because that presents an interesting solution. Any questions about this? So we all agree that the process here is trying to find the area of one of the triangles. Let's suppose, Stephen, back to you. Let's suppose you just did this triangle, which you could do, 5.1 times 2.1 times 1/2. What would you multiply your answer by?
2. Yeah, 16.
Well, or 2, then 8,
Yeah.
yeah, but you'd get 16. So you'd have twice as many right triangles as you do isosceles triangles. Okay. If you started with the apothem, your approach would be similar to what they did, yes? So let's do this again, but do it as starting with the radius. So, Andine, what'd you get for the radius?
5.5.
5.5. Okay. Also, notice the way we solved that last problem, we never talked about the radius. We didn't care about it. Okay, let me get this out of the way. Did you find theta first? Did you work with the central angles?
Yes.
Okay, good. And then found the area of the right triangle? Then found the area of the isosceles triangle, then multiply by 8.
No, we just found the area of the isosceles triangle.
Beautiful. Okay, base times height. Okay, I would present an alternative method. We know that this angle is 45 degrees. Is everybody good with why that angle is 45 degrees? Okay. How long is this other blue segment? 5.5. I would suggest another way to solve that problem would be to find the area of that isosceles triangle using 1/2 AB sine theta. Using 1/2 AB sine theta, I can find the area of this entire triangle directly. I don't need to find the base. I don't need to find the apothem. I get the area of the triangle, multiply by 8, and I'm done. Okay? And there are a lot of small intricacies in solving these problems that different groups use different approaches depending on the approach to the problem. Are we good? All right, I'm going to do one more with you just to make sure we understand this process. Al, pick a number between 10 and 100. 23. This will be fun. All right, you'll need your calculators too, by the way, because you're going to have to help me with this. Al? Apothem, radius, or side length?
Radius.
You're not good at making decisions? Okay, so apothem. And pick a number 1 through 10. Let's make 10. We're going to go right to 10. Okay. We'll do centimeters because centimeters are good. Okay. So we're going to find the area of a regular 23-gon with an apothem of 10 centimeters. Now, I don't know how to draw a 23-gon, but I don't care. Because the only thing I care about is that triangle. Okay, so there's the triangle from my regular 23-gon. By the way, how many of those triangles will I have?
23.
Good, beautiful. So I can find the area of that thing. I take that answer, I multiply it by 23, I'm done. Yes? Beautiful. Okay, do it. If you're, I'm going to talk while you're working. If you're not already doing so, get in the habit of storing numbers. Otherwise, it causes problems with your final answer.
So I stored that.
Each one's 7.5.
What is each side?
180. I'm going to do the 3 practice. I'm going to say, wait, I got 82.
Wait.
I did.
Oh.
didn't really go, I asked all of them. That is. Oh.
Is X,
You do a little bit.
Oh, yeah. I stored the little base of X. And then I said, I need a little base.
Okay, we good? Now, let's talk about, before we get into the actual answer, which I believe is 316.13,
yes.
let's talk a little bit about the effect of rounding answers as you go through the calculation. So first things first, I would imagine you probably calculated this angle alpha, or theta, I mean. How big is theta?
15.6.
So 360 divided by 23 is 15.6. Now, you should store that number on your it's not 15.6, right? 6.5 exactly?
No.
No, but it keeps going, right? Okay, so here's the thing to think about. When you take an approximate answer and you continue to do calculations with it, it increases the error that you have. So for instance, this group back here rounded their answers. Their method was apparently good. They got an answer close, but their answer is off as much as 4. Right? What'd you get, Tommy? 312? Right. So the idea here is to store that number. Then, I'm assuming you divided that by 2 to get this angle? Or did you go to that angle down there? Okay, what'd you do? Divided by 2. 7.8. Okay, then what did you do?
And then, since it's a right angle, I just subtract down 7.8 from the other.
Okay.
And I got 82.2.
Uh-huh.
And then I just did the sign.
Law of sines?
Yeah.
Okay. So, sine of 7.8 over x is equal to the sine of 82.2 over 10. Found x? Found the area of the right triangle, or did you double x to find the area of this?
I multiplied it by 2.
Okay, found the area of the isosceles triangle, multiplied by 23. Beautiful. Any problems? Question?
I didn't have the same answer.
What do you have?
I had 310.27. What?
Did you round?
No. Yeah, I've got the figures.
Are you, did you subtract wrong? Did you hit the wrong button? Do you have really fat fingers and you hit a 6 instead of a 5?
Possibly.
Okay. All right, so have you got this under control? So notice by randomizing this problem and not even knowing what a regular 23 gon looks like, we're still able to find the area of that. Okay, so if you get into something simple, like a hexagon or an octagon or even a square, you could use this method for a square. I don't know why you would, but you could. You should be able to find the area. Yeah? Beautiful. All right, big card.
I have it wrapped up in
Yeah, cooking.